It's math time with Heinz. It's math time with Heinz. It's math time.
Hi everybody, welcome to lesson 7 here, where we're going to talk about transformations of functions. So how can I start with one graph, and if I change the equation slightly, how does that alter the graph of the function is what we're going to look at today. So first we're going to start with shifting and stretching our parent function x squared. Now I know I'm using x squared, but this transformation applies to everything, whether it's a parabola, an exponential function, whatever transformations we do with x squared applies to everything. So let's first start by looking at these functions here. We have x squared plus 4, x squared minus 3. So it looks like I'm adding something on at the end. So what does that do to my graph? So here I have the parent function, the parent parabola x squared there. Notice its vertex is there at 0, 0. And I'm going to graph x squared plus k. So I'm going to add that number on at the end. And if k, let's say, was positive 3, notice the vertex went up to 0, 3. The graph got shifted upwards. If I have a negative 4, the graph went down 4. It got shifted down 4 units. So I went to 0, negative 4. So this k value appears to be a vertical shift. I'm vertically moving the graph up and down the y-axis. That's what this k value does here. So let's write that. The k is a vertical translation, a vertical shift. It's normal. So if you see a plus 3 at the end, that's up 3. If I see a minus 4, that's down 4. Hopefully you don't hear my computer making all these noises like I do. So k is like a normal shift for these graphs. Up 3, down 4. Whatever number you see stuck on at the end of the function, that tells you how the graph is moving vertically. Now let's look at if I stick something inside the function, like x minus 3 squared, and I square that whole thing. Let's see how that affects the parent parabola there. So there's my parent graph. I've got x plus h squared. So let's say I made it 5. Notice the graph is moving horizontally here. But here's the annoying part. See how I have a positive 5, x plus 5? Notice it went left 5, which is kind of counterintuitive. This horizontal shift here is kind of counterintuitive. If I go to a negative 6, x minus 6, notice it actually moved to the right. So h is a horizontal shift, but this one is opposite of what you see. This one is opposite of what you see. So for example, if I see x minus 7 squared, that's actually going right 7 because it's inside and it's the opposite. If I see x plus 1 squared, that's left because it's the opposite, left 1. Notice I'm giving both a direction and how far? 7 right. I'm not just saying right. I'm not just saying 7. I'm going right 7. I'm going right 7. And these two work together. These two transformations work together here. So I can go left and right. I can also go, let me just turn that one back on. I can also go up and down, and I can combine them together and move left and right and up and down. The key thing is, so let's just do a quick one here. X plus 3 squared minus 2. Looking at that, I can quickly say I'm going down 2. And left or right, careful here, that one's opposite. I'm going left 3 units because I'm going left 3, down 2. I can look at that function and tell you immediately. What if I stick a number in front of x squared? So 2x squared, 3x squared, all of those things. What does that do to my graph? So hold on, I messed it up. There's my parent graph there in red. If I go bigger than 1, notice it's getting narrower. The graph is getting narrower because what's happening is my y values are getting multiplied. So this is the point negative 1, 1. Notice its y value is now 3. This is the point negative 2, 4. Well, I'm doing a times 3, so negative 2, 12. Because there's that times 3. Whatever number I have there is my multiplier. That number out front there is a scaling factor, a stretching factor. The graph is getting stretched, so it grows faster. But what if it's like 1/2? Well, then I'm just multiplying by 1/2. So the 0.24, negative 24, becomes negative 22 because I cut that y value in half. The 0.39 goes down to 4.5 because, again, I'm cutting it in half. There's that multiplier, there's that scaling factor that stretches it. What if I go negative? If I go negative, boom. What transformation occurred? A reflection over the x-axis. So the stretching and scaling still happens, but that negative just tells me a reflection occurred. So if A is positive, nothing really happens. If A is negative, if that number out front is negative, a reflection over the y-axis, over the x-axis occurs. Reflection over the x-axis. So if I see negative 2x squared, negative x squared, negative 1/2 x squared, all of those parabolas are going to be concave down versus concave up like they normally are. When my end behavior, when they're both going down, that's called a concave down parabola. If it's bigger than 1, it's a vertical stretch. And it gets narrower. The graph gets more narrow because it's growing faster. It looks skinnier. And if I pick like 1/2 or 3/4 or negative 2/3, those are between 0 and 1, so the graph gets wider. It's a vertical compression. The graph gets compressed like someone sat on the graph. So overall, I can take f of x equals x squared and turn it into this monster over here. So this is my vertical stretch. That number out front tells me how am I wider, am I more narrow? And it can also be a reflection. It can be a reflection over the x-axis if it's negative. So you got to watch out for that reflection over the x-axis. This is your horizontal shift. And remember, this one's opposite of what you see. And then your outside shift, the outside number there is your vertical shift. And that one's normal. So we're going to practice working with these, and hopefully it makes sense. So let f of x equal 2 times x minus 3 squared plus 2. What's the vertex? So the vertex starts off at 0, 0, but what transformations occurred here? Well, what transformations occurred here? I went right 3 and up 2. So that's my new vertex, right 3, up 2. Right 3, up 2. That's my new vertex. Am I concave up or concave down? Well, my leading coefficient's positive, so I'm concave up. Concave up because the leading coefficient is positive. It's an even positive end behavior there, so both my arrows are going up. What's the range? When I talk about range, I'm talking about my y values. Well, my y values are what? Well, 2, and they're bigger than or equal to 2. 2 is as low as I can go, but then I can go up from there. 2, y is bigger than or equal to 2 is my range. What about this guy here? So what's my vertex? Well, what shifts happen? I need to go left 4 and down 5. Left 4 and down 5. There's my vertex. So left 4, down 5. Opposite, the same. Opposite, the same. The inside's opposite. The y value is the same. This guy's got to be concave down because the leading coefficient is negative. So from there, I know it's opening downwards. And my range, well, my y values, range is y, domain is x, range is y. Well, y has to be, where's the vertex? The y value there is negative 5, and I've got to be smaller than it. Y is less than or equal to negative 5. Notice that there's no real zeros here, and I know that just by quickly looking at this sketch right here. Just by looking at this sketch, I can already tell you there's no real zeros there. All right, let's work backwards now. I'm going to give you the shifts. You need to tell me what the function is. So how do I have a vertex of 4, negative 6? Well, I have to go right 4, down 6. So y equals, how do I go right 4? Well, opposite the same. Remember, it's opposite the same and a leading coefficient of 3. All right, I just need to go up 4. So y equals 1/8. I could write x minus 0. That's fine because I'm not shifting at all there. Up 4. 1/8 x minus 0 squared plus 4. Why don't you pause the video and try these next two? I know you didn't actually pause the video there, but let's see what you got anyway. Left 3, up 1. Opposite, inside, outside, the same. The leading coefficient of -2. And then finally, I need to go left 3, but not up or down at all. So y equals -1/4 x plus 3 squared. And I could write plus 0 there, but I don't need to write anything there. That's fine. I'm good to go like that. Okay, so we're going to be doing this a lot in the next few lessons where we're going to be writing the equations, knowing the vertex and the leading coefficient. We're going to be doing this all a lot in the next couple of videos. Like I said, it's not just parabolas, it's any function that we see. So, example, my parent function could be the absolute value function. My new function could be what? Well, g of x is the f function, And what do I do to that f function? Well, I go left 2 and down 4. Done. How do I get this g function? Well, I take the f function, which is this, and go left 2, down 4. Well, I can start with the square root function and do what? I can go, left or right, that's opposite, right 1. There's a negative out front, which tells me to reflect over the x-axis. And then there's a 3 on the outside, which tells me to go up 3. All right, x to the third, it's not just that I can do any function here. Inside the function, I'm going left 1 and up 1. Done. If p of x equals 2 to the x, and this new function s of x equals p, so take the p function and do what to it? Well, I need to go right a, because remember, opposite, and then down b. Direction and how far? Direction and magnitude. How far do I go and which way? So hopefully this was a good review of 9th grade, and we're going to be using these transformations for the rest of the year. See ya.